When my team and I went to the zoo, we all noticed this. And when I closed my eyes, I felt this. These are all patterns, and these repeated patterns becomes rhythm. And nature is nothing if not rhythmic, and its rhythms are many and varied. This is the Rhythm of Life, 7th chapter of the book Nature's Number by Ian Stewart. So what are these patterns? Where can we find these? Do we relate to this? And can we control this?
In the 1870s, the railroad tycoon Leland Stanford bet $25,000 that at some time a shooting horse has all 4 feet completely off the ground. To settle the bet, Edward Muybridge photographed the different faces of the gait of the horse by placing a line of cameras with tripwires for the horse to trot past. And it is said that Stanford won his bet.
Muybridge went on to pioneer the scientific study of gaits. It is a systematic study of animal locomotion, more specifically the study of human motion using the eye and the brain observers, augmented by the instrumentation for measuring body movements, body mechanics, and the activity of muscles. In addition, it is a branch of mathematical biology that grew up with the questions, how do animals move? And why do they move like that? And to explore more variety of rhythmic patterns that occur in entire animal populations, one example being the synchronized flashing of some species of fireflies. Although biological interactions that take place in individual animals are very different from those that take place in populations of animals, there is an underlying mathematical unity, and one of the messages of this chapter is that the same general mathematical concepts can apply on many different levels and to many different things. Nature respects this unity and makes good use of it.
So one of the mathematical concepts that we're talking about is the concept of oscillation applied in biology. Oscillator, a unit whose natural dynamic causes it to repeat the same cycle of behavior over and over again. Why do systems oscillate at all? Why does a caged tiger pace? Its motion results from a combination of 2 constraints. First, it feels restless and does not wish to sit still. Second, it is confined within the cage and cannot simply disappear over the nearest hill. The simplest thing you can do when you have to move but can't escape altogether is to oscillate. Of course, there is nothing that forces the oscillation to repeat a regular rhythm, but a tiger is free to follow an irregular path around the cage. But the simplest option, and therefore the most likely to arise in both mathematics and in nature, is to find some series of motion that works, and it repeats over and over again. And that is what we mean by a periodic oscillation. Many oscillations arise out of steady states. As condition changes, a system that has a steady state may lose it and begin to wobble periodically.
In 1942, the German mathematician Everhard Hoff found a general mathematical condition that guarantees such behavior. In his honor, this scenario is known as Hoff bifurcation. The word bifurcation is used in a particular mental image of what is happening, in which the periodic oscillation grew up from. The original steady state like a ripple on a pond, growing out from its center. The physical interpretation of this mental picture is that the oscillations are very small to start with, and steadily become larger. The speed with which they grow is unimportant here.
There are two biological visible mathematically similar oscillations that could be entangled in locomotion. One is the oscillators of an animal's limb can be thought as a mechanical system's limb assemblies of bones revolving at the joints, pulled this way and that by contracting muscles. Second is the main oscillator of the creature's nervous system, the neural circuitry, that causes the rhythmic electrical signals that stimulates and control the limbs' activity.
A tree with a height of 40 feet that has fireflies on every leaf and has a perfect unison of them, flashing light every 3 times in 2 seconds. The study of Renato Mirolo and Steven Strogatz explained the reason why their flashes are in perfect synchronization. Synchrony is a rule for mathematical models and that every firefly interplay with each other. Firefly is a representation of an oscillation combined together. Their chemical cycle used by every firefly is a model oscillation. That means that the fireflies are represented as a network of oscillation with an entirely symmetric coupling and can be analyzed as each oscillator fully affects other in the same manner.
It's no doubt that living things on Earth has its own unique rhythm.
We get to appreciate every detail of the movement, learning that this can be applied in mathematics, reasons that can be seen in the surroundings which can amazingly be applied in mathematics.